Okay, here's another video on the symmetric slab. So this is a continuation, and what we have is so far is we have our what's called a mode diagram or a mode plot for the symmetric slab. What we're going to do is we're going to consider fix N1, N2, the indices, and we're going to fix lambda and D also now. Now we're going to plot theta versus the dimensionless waveguide thickness, D by lambda, and we're going to plot theta from 0, or from the critical angle up to 90 degrees. The critical angle depends on N1 and N2, and so making this whole plot is done knowing N1 and N2. And what we found is that we had a number of solutions that look something like this, evenly spaced along the D by lambda axis, something like this. And we found that we could take our particular lambda and D and plot them and find this value. And from this graph then we can read off the number of modes, that exist, and their theta values. These theta values are called zigzagging angles. Okay, so this gives us a fairly complete description of our waveguide. So for example, if this were my actual D over lambda value, then I would find these three modes and they would have these three zigzag angles. And I'll call them theta 0, theta 1, and theta 2, because this is the M equals 0, 1, 2, 3, 4. These are how the modes are labeled. Okay? So this is what we can do with that mode plot. Okay? What I'm going to do is now redo the mode plot with a different vertical axis. And I'm going to do it with what's called the effective index. And let me give you a quick derivation of what the effective index is. Let me go ahead and draw my waveguide again. N1 greater than N2, N2 out here in the cladding. And I'm going to go ahead and draw my zigzag ray with its zigzag angle theta. And I'm going to suppose now that this direction is the direction of a propagation vector k, and that the k vector has a magnitude equal to our k, which is 2 pi n1 over lambda, where lambda is the free space wavelength. Okay? And that the direction of k is in the direction of propagation of that that zigzag ray. Okay? What I'm going to do is I'm going to define beta, which is k sine theta. And this is called the longitudinal wave number. Okay? And so it turns out that it is the component of k along the direction of the propagation of energy in the waveguide. Okay, even though this zigzagging angle looks like it's bouncing back and forth, in the end energy is propagating in the direction of the waveguide. Okay, and what we can do then is we can now, and I'm not telling you exactly why this is such a great thing. The reason it's such a great thing is that our Z dependence of the field solutions, the E field solutions of these modes, E is going to be proportional to the sine of beta Z minus omega t. Okay, so this is now acting the way K used to. When we had free space, we had Kz minus omega t, and now we have beta Z minus omega t. And beta is the component in the direction of energy propagation, and so that makes sense because we want something that's characteristic of the Z direction here, and so beta makes sense there. It turns out that in free space, if we take the ratio omega over K, we have 2 pi f divided by 2 pi over lambda, which turns out to be f lambda, which is c, which is the propagation speed in free space. Inside the waveguide, we're going to go ahead and use omega over beta. And we're going to write that this is equal to 2 pi f all over, now beta is 2 pi n1 sine theta over lambda. And look, this becomes c over n1 sine theta. And it turns out that this looks like what we get inside of a medium. Inside of a medium we would get c divided by n. Here we get c divided by n1 sine theta, and it turns out that n1 sine theta is our effective index. Okay, because it characterizes the propagation speed. I guess I have to keep these guys in their own spaces here. Hope you can read that. Sorry. So N effective characterizes the rate of propagation of energy along the Z direction in the waveguide. Okay? Maybe this is the Y direction. Okay, I will go to the next video for the next slide. Thanks.